evening and welcome to the Science Slam. I realise circumstances are a little bit different this year, but I know we have some people watching who have watched the Science Slam in previous years when we were at Cottiers, so welcome back. If you're new, hello, my name is Sian, hi, and I'm your host for the Science Slam. If you haven't been before, the basic premise is that we have some amazing researchers. When we first met them, they were doing their PhD, and now a lot of them are grown-ups doing postdoc saving the world stuff. And we asked them to talk about their work in an entertaining way. Throughout the years, we've visited volcanoes, we've dealt with blood, we've had computers, we've had statistics, we've had psychotherapy, we've had nanotechnology. We have explored all of the beautiful, weird and wonderful bits of science that you can explore in your PhD at the University of Glasgow, Science and Engineering grad school. So, because obviously everything is different now, we have brought along some of our favourite alumni to give you a little sample of what they're working on now or what they worked on during their PhD. All you have to do is sit back and relax. Normally we would have some voting, but this year they're all winners. We're all winners just for surviving this. And so we're going to have a little bit of a quiz later on. We're going to have a little chance to make some cocktails, which I will personally be making from the random crap I found in my kitchen cupboards. The end of the show could be really interesting. And so we would love to know where you're watching from, what you're doing, and how you know about the Science Slam. So you can leave a comment on YouTube. I'm pointing. I don't know where your comment box is. There, maybe? You can also tweet us if you're that kind of person using the hashtag SciSlamAlum. We're on Instagram and on Facebook as the University of Glasgow Science and Engineering grad school. If you search that, you should find it. Tell us who you are. Tell us where you're watching. We know that we had people signed up to join us from over 30 countries. The graduates and the researchers who featured have come from all over the world over the years. We've been doing this since 2013 and have seen some amazing talent come through and then go on to do really world-changing things. We hope that you enjoy this evening. If you have any questions or any queries, put those in the chat box as well. Hi, you've got a few comments already. Hi, Claire. Someone's proud of Angela. She hasn't even been on yet, and she's got pride. That's very lovely. So, get yourself comfy. Get your... you have a cocktail, which can just be an intriguing cocktail of a tea bag, some hot water, and some milk. We'll totally call that a cocktail for now. We just need you to enjoy this evening. Our first presenter, we are very excited to welcome back, was won our first ever Slam back in 2013. It's been run at Cottiers all the way back then, thanks to the hard work of Heather Lambie from the grad school and our tech support throughout the years, who has been Jamie Gallagher. If you hear a mysterious voice telling me that I'm doing something terrible, it's Jamie. So way back then, Lewis had brought a laser harp on stage, which looking back may have been completely dangerous. Who knows? We flirt with danger here at Science Slam. But this year is going to be talking about seeing through skin through nanotechnology. I realise we can't really do applause with the way it's doing this year. So instead, can you just either comment some applause, look at someone or in your house or an object you love in your house, just give them a reassuring smile to kind of signal your excitement at the start of this presentation. And with a little applause, do a massive smile as we welcome to our Science Slam stage, Lewis, talking about seeing through skin with nanotechnology.
Hello, I'm Lewis Kenzie. I'm a research fellow at the chemistry department at Durham University in England. But I used to be a PhD student at Glasgow. And my PhD was all about measuring blood oxygen levels, figuring out where the blood was going and how the oxygen was being used by different parts of the body so we could help understand what was going on in normal health and in disease. I was in the physics department, which was a really strange experience because some days I actually got to shoot lasers at blood, and that legitimately made me feel like a bad scientist. Most of the time, though, things were a little bit more down to earth because the way we measure blood oxygen was quite simple in a lot of ways. It involves a colour filter and a camera. So, I have here some blood. This is just water and food colouring. Lockdown didn't get quite that boring yet. And what we do is we get our blood, we put it in front of our camera, and we get a red filter and take a photograph of the blood. Then we get another filter, blue or green, for example, and we take photos with both colour wavebands. That way, we can pinpoint what the colour of the blood is. And that's really important because the colour of blood depends on how much oxygen is in that blood. Blood with lots of oxygen is a bright strawberry red colour, whereas blood with less oxygen is kind of a dark scab red colour. Now I should say at this point, human blood and mammalian blood is never blue. That's a misconception. If you want to know more about that, you can ask me a question in the comments and I'll answer after the show. After my part of the show. Anyway, so that's how we see blood oxygen levels with different colour filters. There's a slight problem. In order to measure that blood, you had to be able to see the vessels that contain it. And that would limit where we could measure blood oxygen levels. And we'd often do it in the eye. We'd take a photograph of the back of the eye and the retina, and we'd measure blood oxygen levels there, which would tell us things about diseases like diabetic retinopathy or blood vessel occlusions. But we couldn't measure blood oxygen levels deeper inside the body where a lot of diseases manifest. And that was a bit frustrating, but it was a limitation of the technology. I wrote about it at the end of my thesis. This has been a problem for decades. I couldn't solve it. I wasn't there to solve it. Time to move on. So I ended up moving on and getting a job at the University of Leeds, where I was working on a type of sensor technology based upon nanoparticles. Now, nanoparticles are tiny little crystals. They are so small that you could fit 1,000 of them onto the width of a human hair. Now, one night I was sitting in the pub listening to science, having a drink, maybe as you're doing right now, and I had a bit of a eureka moment, which goes to show that having a drink and thinking about science does work. And the eureka moment I had was that I could make these tiny little nanoparticle sensors function like molecular dimmer switches in the presence of oxygen, and that they would give off loads of red light when there was lots of oxygen, and they would go dim and darken when the blood oxygen levels were low. And the important thing with these sensors that made them special was that they gave off red light. I can give you a little demonstration. Why? So I have here a bicycle lamp. I'll get my blood back out. If I shine the white light of the bicycle lamp through the blood, you'll see that only the red light gets through, and that the green light and the blue light is absorbed by the blood. And so while we have many oxygen sensors that work with blue or green light or ultraviolet light even, we don't have many that work with red. And this red light can even see through several centimeters of tissue. So for example, take this white light torch, put it behind my finger, you should be able to see that only the red light gets through. You can try that at home with your phone camera torch. It's quite fun. You might be able to see some of your veins. But not only could we see through, for example, several centimeters of finger tissue, you could see through, for example, an entire mouse, the kind of mouse that is used in essential biomedical research. And this gave me an idea, which was you could actually use these nanosensors to help cut down on the number of animals sacrificed in biomedical research. Because you see, when biomedical scientists are having to do essential research to understand, for example, how a tumor grows inside the body, they normally have to reach for the dissection kit, which isn't great. The poor mouse meets its end under anesthesia, and the scientists only get a single data point at a single point in time. But with these nanoparticle sensors, what we could do is inject the nanosensors into the bloodstream, let them circulate around till they reach a particular point of interest, for example, a tumor, and then we could read out blood oxygen levels from that tumor using only the red light. You wouldn't even have to touch the mouse. And not only would this be better in terms of time and cost, but we could get better data because that little mouse could be alive for days or weeks as the disease progresses, and we could get a better idea of how things develop with time. And of course, the mouse gets to live. So that's just better all round. It's a win-win. Now, I was supposed to be working on this research in about 2 weeks' time. I was supposed to be making these nanoparticles in a chemistry lab, but the lab shut for a little while due to COVID-19. But in the meantime, I just want to leave you with this idea. Remember, seeing red isn't always a bad thing. Enjoy the rest of the show.
Hi, everybody. Hang on, let me check. Everyone can see me again. Hi, now, I know that they were filmed before. Could you give us a wee comment if it's sounding okay now? I think that was primarily my fault from leaving my mic on when I wasn't meant to. And thank you so much to everybody who has commented so far. We have got people watching from Ghana, Nigeria, America, Canada, Poland, Maryhill, all corners of the world. That's it. That's the whole world, from Ghana to Maryhill. Everything. It's so nice to have you here, and thank you so much, Lewis, for saving the mice. Really appreciate that. Those mice need you. You're a mouse hero. So I think that is lots of people saying great first presentation. The sound seems to be okay now. So we will continue on our journey through the mysteries of science. Next up is another one of our favorite Science Slam performers, and we're so excited that she's joining us here today from Ghana. I think her mom is watching. So hi, Angela's mom. Your daughter's really clever. So Angela did her PhD in mathematics at the University of Glasgow, and she's now doing postdoc work in Ghana. And she is going to talk to us a little bit about mathematics and COVID-19. We're really intrigued to see what she's going to tell us about. Please welcome, with clapping your dog, clapping yourselves, or just smiling, please welcome Angela.
Feel that nation. It's been too, baby. Enemy see them no be God, then once see my downfall, but the boy them know the flop. Me across my hands I chalk. Zanku.
Hello. Welcome to Science Slam Alum. 3 years ago, I was on this stage doing the famous Zaza dance. 3 years on, I've graduated with a PhD in mathematics and returned to my home country, Ghana. Hooray! And currently, I'm a Ames Google AI postdoctoral fellow at Ames, Ghana. I remember updating my profile on LinkedIn, and my friends started asking me, Angie, do you work at Google? How did you get in there? No, I don't work at Google yet. Hopefully, this talk will get me a job there. We've heard this, the future is AI, and we can transform our society with AI. But what has the role of AI been in the fight against COVID-19? In the next few minutes, we are going to go through a crash course on mathematics for machine learning. Hopefully, at the end, you have the necessary tools to fight against COVID-19. Okay, so let's say I am doing a survey to collect data on COVID-19, and I'm asking 3 questions. The 3 questions are this: how often do you eat fruits and vegetables? Because the more you eat them, the more your immune system is boosted. The second question is, how many people live in your home? Because the number of people who live in your home affects the transmission rate. And the third is, how often do you step out? Okay, so when I collect all these information, so I'm going to store them in this container. Okay, so for me, I eat fruits and vegetables just once in a day. So I'll store that here. And I have a very large family size, so there are 9 people in my home. So I'm going to store that here. And finally, I step out only once in a day, so I'll store that here. Okay, so let's suppose I get a virtual volunteer who comes to give me answers to the same questions. And for this volunteer eats vegetables twice in a day, so I'll store 2 here. This volunteer lives with one other person, I'll store 2 here. And this volunteer goes out twice in a day, so I'll store that here. Okay. So if I want to add the data of my volunteer and that of mine, I can do that taking into account that each row measured a specific question. So I can only enter the entry in my row here to the entry in the volunteer's row there. Okay. Now, if I assume that everyone in my household has the same eating and outing habits, so everyone in my household eats vegetables and fruits once in a day, and they also step out once in a day, then their container will be the same as mine. So if I want to find the total of everyone in my home, I'm going to scale my container by 9. So in mathematics, we call any object that you can add or scale vectors. Hooray, you're done with your crash course in linear algebra. We are moving to the next course. Now, if I put this object on this, will it fall? No, right? But what if I slant it this other way? Why? Why does the object behave differently in these different positions? It's because the slant of the object is different in these 3 positions. And in mathematics, we call the measure of the slant of an object the gradient or the slope. And multivariate calculus is the area of mathematics which studies slants and its applications. Hooray! So you are done with your crash course in mathematics for machine learning, and now you are moving to the final part of the course. Now let's consider the globe and the map. Are they the same? Is every point on the globe represented on the map? Probably you've heard that the map is 2D and the globe is 3D. So that should ring a bell for you that they are actually not the same. So D there represents dimensions. So dimensions is the number of attributes you are collecting. So dimensions is the number of rows you have here or the you have here. In real life, data is in very high dimensions, so you can have a high dimensional. But currently, we can only visualize data up to 3D. So how do you extract the relevant dimensions from 100-dimensional data to 3D to visualize it to see how your data looks? You can do this using linear algebra and multivariate calculus, using it to extract the principal component in your data, and we call that principal component analysis. Congratulations, you are done with your crash course in mathematics for machine learning. So how did I end up here? Last year, I had the opportunity to teach this course at AIMS Ghana and AIMS Rwanda in the African Masters in Machine Intelligence program, which is sponsored by Google and Facebook. This is the first master's program in machine intelligence on the continent of Africa, and it is training Africans to use AI to solve the challenges that we face in agriculture, healthcare, and few. And I am grateful to AIMS Ghana and Google AI for this amazing opportunity they've given to me to change that. Bye.
Thank you so much, Angela. Someone in the comments wrote that they feel smarter just for watching, and I totally agree. This is my little annual education watching the Science Slam. So it's been fantastic hearing from people so far. Hello, we have someone watching from India as well, and Angela's mom. I hope you're very proud. She did great, right? So normally during the Science Slam, it takes place in Cottiers, which is the most beautiful venue. It's an old church with a vaulted ceiling, with fairy lights, which I tried to recreate with these old Christmas decorations. And we always have a Sci Slam cocktail. So at this point, I would invite you, if you need to pop to the loo, go get yourself another drink, try maybe making yourself a cocktail, which does not, of course, have to be alcoholic. Originally had been to make a beautiful science-based cocktail to inspire and create a kind of art through mixology that I was going to demonstrate. But we're in self-isolation because my housemate has some symptoms. So I couldn't get to the shops. So here are the random things that I have in my house that I thought we could enjoy together during this cocktail hour, cocktail 5 minutes. So I found some juice, some of this vodka brand, which I won't show, but for people who live in Scotland, they will know it. It's the kind of vodka that gets drunk in elegant surroundings like parks and bus stops. I also have some white rum and some brown rum. I mix those things together, absolutely. If you would like to tell us in the comments what you are mixing together, I would appreciate inspiration. But I think in the interest of someone who's drinking Iron Brew, yes, excellent choice. For anyone watching from overseas who has not experienced Iron Brew, I want you to imagine the sweetest nectar in the whole world. Imagine that nature created nectar that was the kind of orange that sort of shouldn't really exist, and that the minute you drink it, your teeth immediately feel furry and like they're about to fall out. And yet, you cannot stop. You will not stop, because that is the joy of Iron Brew. So, in the interest of science, I thought I would start my cocktail with this bottle that I found in my cupboard. Now, there are two things that be. I'm pretty sure some bramble vodka that my friend made for me. As a kind of wholesome, organic, get drunk with hippies drink. It might be Calpol. Not sure. That's going to be what I start my cocktail with. We have just got some water and lemon juice. That's how I was expecting more ingredients in there. Water and lemon juice. I feel maybe just water would be okay, but that's good. You're like a pancake, just giving yourself a topping. So just before we get the next act on, I should explain. Okay, let's see how this cocktail goes. I'm going to add just a tiny bit of rum to it as well, and then I'm going to mix it in the spirit of Science Slam. I might not be able to speak after this. So to explain why I have a £10 note behind me as well. I'm not in my house, but I'm very lucky that I had to go in lockdown elsewhere, but I got to go in lockdown in the beautiful town of Burnt Island. For people not from Scotland, Burnt Island is a wee town on the Firth of Forth. It is very beautiful, and it's also home to this lady here. So this is a Scottish £10 note. I am staying right here. That's where I'm staying. This is Mary Somerville. And she is in the background because it's because of Mary Somerville that we have the word scientist. Mary was a researcher and had the role that would have been previously known as being a man of science. But as you can tell from her lady hat, she was a lady. And so the more gender neutral term of scientist was born. And Somerville College in Cambridge, Oxford, was named after her as well. How cool is that? And she rocks a hat. That lady is everything I crave. So this is going to be the Science Slam Cocktail 2020. It is unknown red liquid with rum. I should say my backup cocktail is beer, which will probably be what I end up drinking. But just to say a little something, I know the world is in a strange place at the moment, and it can be, a lot of people are feeling quite disconnected from not only each other, but from art and entertainment and information that feels reliable and true. And the Science Slam has always been a real highlight in a lot of people's calendars because it's about fun, about laughter, about coming together, about celebrating education, celebrating information, and celebrating what happens when we exchange those things, when we tell each other our ideas and inspire each other. And I am not a scientist. I did a master's in creative writing, which means I can read stories really fast and have quite nice bubbly handwriting. But I have learned so much from these presentations, and I'm so proud to be able to introduce some of these people here again who are genuinely making the world better. So even though we are watching from all over the world and we are physically so far apart, even if we're only a few miles geographically away from each other, I really hope tonight feels like an opportunity to come together for just over an hour and experience what it's like to learn together. And so in the spirit of that, as we say in Scotland, wish me luck, slange, gambe, cheers. Oh! That's really terrible. I'm going to start with beer. So I hope you're enjoying your Science Slam cocktail, whatever you have decided to make for yourself. But we are very thrilled to welcome back our next presenter. Sophia has just submitted her thesis. Sorry, Sophia, it's on a screen just below me. Sophia, do you know yet what your you haven't heard back from it yet. You just submitted. It's very exciting. So she's done a PhD in computing science. She has been named a future world changer by the University of Glasgow. And I think you'll see why after you see her presentation. Tobias going to be talking to us today about matching algorithms. And I think it's going to be really interesting to see what she tells us. So please pat your dog, raise your glass, smile at an object, and welcome Sophia.
Hi everyone, I hope you can hear me. Fingers crossed you can. Hello, my name is Sophia Olashebikon and I'm completing a PhD in computing science at the University of Glasgow. It feels good to be back as a presenter at the Science Slam alumni event. The first time I took part in Science Slam was in 2008, and at that time, I was in the second year of my PhD. Now I've submitted my thesis. Yay! Big milestone, right? Yeah. So for the next 5 minutes or less, I'm going to be sharing with you a condensed version of what I spent the last 4 years working on. The class of problems I tackled during my PhD occur naturally in the real world. They are referred to as matching problems. And just in case you're thinking about the online dating kind of problem, no, that's not it. I'll give you 4 examples to illustrate what I'm referring to. One of the examples is the allocation of youth to gap year programs in Israel and in my home country, Nigeria. The agency in charge of this named the gap year programs NYNC, which is the National Youth Service Corps. The second example is the allocation of junior doctors to hospitals. Third example is the allocation of donor kidneys to transplant patients. And the fourth example is allocation of students to dissertation projects in universities. Now, the common trend in all of these applications is that the agents involved, and by agents, I mean the youths, the students, the doctors, the agents involved have some form of preference over the possible outcome, and they also have capacity constraints. To make things clearer, let's take a look at a very small example of allocating students to projects. Now, there should be an example that pops up on the screen, and I'm hoping that shows up. So the example on your screen consists of 7 students and 4 projects. The students are Alex, Ben, John, and so on, and the projects are algorithms, data science, modeling, and systems. I hope your favorite course is there. Now, each of the students lists their most preferred project, and each project also has a capacity which tells us the number of students they can accommodate. So for example, algorithms can accommodate 2 students, and the preferences of Alex is algorithms and data science. That makes sense, clear. Moving on. Now, the big task for us is to compute an allocation that respects those capacity constraints, that respects the preferences, and most importantly, an allocation that is fair for everyone involved. Now, suppose there are, say, less than 10 or 20 agents. We can attempt to make these allocations manually. However, on an annual basis, thousands of youth wish to be deployed in Israel and in Nigeria, and over 40,000 junior doctors wish to be assigned to hospitals for their residency program in the United States. Now, how then can we compute these fair allocations in the real-world applications without spending ages on the problem and without wasting human resources? Well, you can think, why can't we use computers since they are super fast? You are not wrong to think that. Computers are fast. They'll crunch our problems in seconds, but they are not that smart. We have to tell the computer what to do in a language that it understands. And this is where my research comes in. So what I do is design a set of instructions that the computer will follow to compute a fair allocation from the given matching problem. And this set of instructions is what we refer to as algorithms. And to design these algorithms, I use tools from an area of discrete mathematics known as graph theory. Now, for those that were not at my previous Science Slam presentation, I'm going to give you a crash course in graph theory so that you have an idea of some of the jargons that we use. Now, let's take a look at the previous example I showed you. That's the example of allocating students to projects. And I hope that's coming up on the screen now again. Fingers crossed. From an area of discrete mathematics known as graph theory. To approach this problem, the first thing we do is place the students on one side and place the project on the other. And then students each project. In graphic, using students to project. For example, we connect the vertex representing Alex to algorithm and the vertex representing Alex to data science. And then we do the same for all of the students. As edges, take note of that. And this structure that is made up of vertices and edges is what we call a graph. So the next thing we do is study patterns in this graph, and this aids the design of the algorithm. I wish I could continue with how we study the patterns, but in this part is why my PhD took almost 4 years. So in that 4 years, I reached several results which will be useful in real-world applications of mapping problems. Interestingly, these applications goes beyond the examples I mentioned earlier. So during my PhD, I came across an application of the students project algorithm, which you can see on the screen. And this application is precisely in an engineering context. You wouldn't believe how a student project allocation algorithm could be useful in an engineering context, specifically in the cellular networks, where the goal is to assign network users to channels at base stations. And these are some of the things that got me through the PhD, just knowing that the result from my research has an immediate impact. Other factors that got me through is the amazing support I received from my supervisor and colleagues here at the University of Glasgow. And the fact that I also get to explore different parts of the world every now and then to present my research. So I've visited cities in Morocco, Canada, the United States, Switzerland, India, just enjoying the food and the culture. On a final note, I hope to keep improving on my skills by getting involved with more research motivated by real-world problems. So if you have any comments or some exciting projects that requires my expertise, feel free to drop me an email or a message via Twitter or LinkedIn. You can find my contact on my website, which should appear on your screen. If not, www.sofiatolaosebikon.com. Thank you very much for your time and for listening. I hope you enjoy the rest of the presentation. Bye.
Thank you so much, Sophia. That was fascinating and 4 years well spent, especially as you said, there was such an immediate effect on your research. That's fantastic. Top work and good luck after submission. Next up, we have Anne-Marie, who did her PhD on impact trainers and impact craters and is now training actual astronauts. She is going to be talking to us today about impact craters and asking the question, are they a nice place to live? Please do whatever you've been doing to welcome our next scientist and welcome Anne-Marie.
Hi everyone, it's great to be back at Science Slam. Last time you saw me was 3 years ago when I was a PhD student studying impact craters, not impact trainers, which would also be kind of cool. And at that point in time, what I was doing was trying to figure out how old impact craters are, using something called geochronology. But if we fast forward till now, 3 years later, I've finished my PhD, became a postdoc. And for my postdoc project, still at the University of Glasgow, what I'm looking at is trying to figure out, would impact craters be a nice place to live? Maybe. But before we get into that, I think we should talk about what impact craters actually are. So if you picture the moon, or if you have no imagination, look at this moon right here, and you see all these small circular features. There we go. Those are all impact craters, and they're the result of a rock in space coming and hitting the moon, moving very fast. And they excavate a very, very large hole. And they're the surface feature on the moon, but also on Mars, and not the dominant feature, but still a major feature of Earth. In fact, I know we have some visitors from Ghana. There's the Basumti structure in Ghana. There's the Lonar structure in India. There's just hundreds in Canada. Put all those in. There's about 200 100 on the planet, so I won't show you all of them. It gives you an idea that they're spread out all over the globe. So let's talk for a minute about how impact craters form. Out in space, you have rocks floating around. Now, there is a small rock in there, but I'm going to leave it in the case, mostly so I don't lose it, but also so you can still see it. And while it hasn't landed on Earth yet, it's still labeled, in my example, it's still labeled a meteorite, because of course, in real life, it has. So, there's a nice rock in space. If it gets too close to a planet, it gets pulled in by its gravity and comes crashing in. And can make a really large hole if it's big enough. Now, it can be quite a dramatic situation. So let's take a slightly closer look. Ah, this is a good land. We shall call it this land. I think we should call it your grave. Curse your sudden but inevitable betrayal. But what's that behind you? I'm not going to fall for that. Thank you for that hyper-realistic recreation of the formation of the Chicxulub impact structure, guys. As you've seen, the impact structures, craters, cause a lot of destruction and chaos when they first form. And that's because you have all this kinetic energy from your space rock hurtling towards a planet. And then when it hits, all that kinetic energy gets transferred into things like heat and into expelling large amounts of material into the atmosphere. So locally to the impact, you end up with, well, a big hole, lots of melted rock, that's lots and lots of heat, forest fires, wildfires everywhere. There's tons of dust and soot in the atmosphere, which can make it really, really cold, cause all the plant life to die, cause our dinosaur friends to die. So from that perspective, the question, are impact craters a nice place to live? Our friends the dinosaurs would say, no, they're terrible. But what if we wait a couple of years for things to calm down a little bit? Well, what you have is still quite a lot of heat and, at least on Earth, interaction with water. And one thing that we found on Earth is that everywhere that you have heat or any source of energy interacting with water, you find life. But then again, on Earth, we find life almost everywhere. So what about somewhere like Mars? Mars is a lot colder than Earth, but we do now know that there is water on there, especially up at the poles and under the surface. So if you deposit a huge amount of heat into the surface of Mars, you'll get water, you'll get heat, and potentially somewhere that life would like to exist. And when I'm talking about life here, I'm not talking little green men, I'm talking microorganisms. So things that are much, much smaller, for example, than the size of a human hair. So how do we study these things? Well, we can make a small slide. This is called a thin section. It's a very, very thin piece of rock that's been polished down so it's so small that we can see through it. And I'll give you guys a closer look. And maybe Jamie, could you go to super zoom mode? So what you're seeing now is this sort of curly feature that you find in a glass in an impact rock. And what it looks like to a lot of people is that there was bacteria in the water surrounding this rock, living off the heat. But then when the bacteria needed something to eat, it started eating into the rock and left these little tunnels behind. And there's a lot of debate about whether these are actually biogenic, or biogenic means life made them, or if they could just be really weird crystals. So we can come out of zoom mode now, Jamie. So my work is on looking at these features and trying to decide or determine whether or not life actually formed them. But I can't give you an answer yet because I've really only just started the project. So you'll have to tune in later to find out. Thanks.
Thank you so much, Anne-Marie. And as someone pointed out in the comments, was that a science presentation or was it incredible interactive theatre. Loved it. Not enough dinosaur models in the world. I think we can all agree. Guys, there's 2 things I need to tell you. One, I don't drink very often, so in the past 10 minutes, I have twice grabbed that red glass thinking it was Ribena and taken a massive swig. My life is unraveling before your very eyes. And also my dad's watching. So if everyone can say hi to Clive Bevan's watching. That's exciting. He can't normally see them. So it's nice that he can join us here this evening. Thank you so much, Anne-Marie. We appreciated that and hearing all about craters. And now we're going to go from craters to volcanoes. And I've got Richard joining us again, who is currently Royal Academy of Engineering. He's a Royal Academy of Engineering Research Fellow at the James Watt School of Engineering. Very fancy. And he's going to be talking to us about how to forecast a volcano eruption just using a piece of string and a stopwatch. Intriguing. And so could you please put your hands together, glasses together, cats together, and welcome Richard.
Hello, everybody. Thanks a lot for having me here. It's been, 6 years since I first did Science Slam. And I've been asked to give some highlights of what I've been up to since I won the event in 2014. I think on paper, my biggest achievement was having the work that my supervisor and I did during my PhD named as one of the top 10 breakthroughs in global physics for 2016, which was incredibly gratifying and kind of astounding. But I think personally, the most overwhelming thing was the moment that I realized the practical impact that this work could have. And this happened 3 years ago when I found myself on Mount St. Helens in the USA on a pretty peaceful, sunny afternoon. But 37 years before that, there was quite a different scene there. At 8:32 a.m. on Sunday, the 18th of May, 1980, there was a small magnitude earthquake. And seconds later, a mountain 3 times the size of Ben Lomond all but exploded. In a matter of seconds, an entire side of the volcano and most of the top of it collapsed, releasing 1,600 times more energy than the Hiroshima bomb. Several glaciers melted, causing pretty catastrophic waves that ripped down valleys up to about 50 or 100 miles away. And in the blast radius, enormous trees were kind of snapped at their roots and buried in the ground, and almost anything or anyone in this area was killed. Had that mountain been Ben Lomond, don't worry, it couldn't be Ben Lomond, Ben Lomond won't erupt. But had it been, then Glasgow would be on the edge of that blast radius, and you could wave goodbye to Milngavie, Bearsden, and Maryhill, where I am now. So there aren't too many ways that you can try to forecast an eruption. But at that moment, 3 years ago, I knew that I was working on something that could help to do this. Extremely accurate gravity sensors that you can use to see things underground. So gravity, here's a quick primer about gravity. Don't worry, it won't be too technical, but everything with mass has a gravitational pull, and this pull is very weak. So you only normally notice it from huge things. Like the feeling you're feeling right now, the entire Earth is pulling you into your seat. But everything around you is also gravitationally attractive. So if you imagine we were standing a meter apart right now, I know that's fairly hard to imagine and kind of illegal given the current restrictions, but in that situation, we would have a gravitational attraction between us that will be about 2 billion times smaller than the one each of us will be feeling towards the Earth. But in theory, if you could make an accurate enough gravity sensor, then you could start to be able to see the pull of smaller and smaller objects and distinguish them from their surroundings. And by scanning a sensor like this around the ground, you'd be able to see changes in density underneath the Earth, like magma, which has a different density than the surrounding rock, moving quickly but inexorably towards what could seem to be a quiet volcano. Again, not Ben Lomond isn't a volcano, don't worry. So how can you engineer a means of measuring gravity? Well, one thing that you can do is to use a pendulum. So what controls the speed at which this pendulum moves back and forth? The first thing is the distance between the pivot and the weight, in this case a potato. If it's longer, then it moves slower, and if it's shorter, it moves faster. So that means that if I fix the length of this pendulum, then the timing won't change, right? Well, wrong. Because there's a second factor, gravity. If the value of gravity changes, then the timing will change. If I were on the moon, then the gravity would be smaller, so the pendulum would move more slowly. But the opposite would be true on Jupiter, which has a much stronger gravitational field. But we've already discussed that you also get these small variations on Earth. I have a gravitational pull, you have a gravitational pull, and so does magma. And at home, using this potato, which is not a sentence that I use very often in the lab, I could measure the length and timing of my pendulum perhaps accurately enough with a, like a smartphone stopwatch to tell me whether I was on the moon or the Earth. But that's not particularly useful. I've got a reasonable idea where I am at the moment. However, if I can measure my pendulum's length and timing down to billionths of a meter and billionths of a second, then I could measure the tiny changes in gravity that we want to see. So instead of just knowing what planet I was on, perhaps I could start to see the influence of you sitting next to me, or the magma rising beneath my feet. Now, this is what I spend my time doing. I try to find ways of making small and cheap pendulum gravity sensors using microscopic things, mechanical devices that you find inside your smartphone. And then I try to measure the length and the timing to a precision that means that we can see these tiny variations in gravity, which often means that we need to measure these movements to less than the width of an atom. It's quite precise stuff. So on a volcano, if I wanted to have an image of what was going on underneath, then having one gravity sensor would be like having a single pixel on your mobile phone camera. So not that useful. But since our sensors are small and cheap, you wouldn't have to have just one. You can make tens or hundreds or even thousands of these things for not a huge amount of money. And you could create the first multi-pixel gravity imager in the world. But this isn't just theory. If it weren't for the virus, then this summer we were supposed to be installing a multi-pixel gravity imager like this around one of the most active volcanoes in the world, Mount Etna in Sicily. But times will change, and the network will be built, at which point we'll be able to see the inside of a volcano with entirely new eyes, and it's going to be an incredible view. So thanks for listening, and if you've got any questions or you want to know the maths behind this or anything crazy like that, then write something in the comments below. Thank you for listening.
Thank you so much, Richard. Thank you so much for that amazing presentation. And if you do have any questions, leave them in the chat box and Richard will try and answer them. But before that, it is quiz time. We are very excited to be having a special Science Slam quiz. There's normally a lot of chat that happens around the Science Slam table, so this is instead of that. There are two ways that you can join in with the quiz. So there should be a link in the chat box now, so you'll be able to join in and play along with us in live time. You'll find out instantly if you were right, wrong, and how you're doing compared to other players. The faster you can answer, then the points that you will get. So if you click on the link and open it in a different browser window, then that will work. Of course, you can just listen to me reading out the questions and yell the answers at your dog. And if they bark twice, you're right. If they bark once, they love you anyway. Don't worry about it. They think you're amazing. So I'll give everyone a couple of seconds to choose whether they click on the link or whether they're just going to join along with their dog and just pretend they knew the answers anyway, which is what I do when watching University Challenge. Go, yeah, I was about to say that. Yeah, they said it a bit quicker than me, but yeah, I would have pronounced it slightly differently, but yeah. So I'm going to assume that everybody has got it. I should say, because I'm reading out the questions, I can no longer see the chat box, so I hope everyone's okay there. I can't hear you anymore. I'm in a volcano. So, are we ready for question 1? Which waveband of light travels furthest through skin tissue? Ultraviolet, blue, green, or red? I've got a little clue about this in Lewis's talk right at the beginning. Which waveband of light travels furthest through skin tissue? Ultraviolet, blue, green, or red? You've got 5 more seconds to answer. And the answer was red light. Red light travels furthest through the skin. Test it out by shining a white light through your fingertip and doing your best E.T. impression. You can sit in a wardrobe. If you like, get in the basket of your friend's bike. I think we all just want to phone home right now. Okay, we're heading to question number 2. So click through or just slightly adjust yourself if you're not doing it on the website. Question number 2. What is the loudest recorded noise in human history? The launch of Saturn V rocket in 1967, the Tunguska meteor landing in 1908, the new campus building works in 2020, I think that is a little niche one, or the eruption of Krakatoa in 1883. What do you think was the loudest? I'll give you 5 more seconds to answer. And the answer was, I just realised I don't actually have the answers on this. Jamie, if you're listening, could you put the answer on the chat screen for me? Because the loudest was recorded at 310 decibels. So the loudest noise ever was 310 decibels. For reference, 180 decibels causes death of hearing tissue. And, so it's Krakatoa. I didn't read it right. It's okay, Jamie. Krakatoa was 3 million times louder than the volume, which would destroy hearing tissue. There you go. Okay, we are heading over to question number 3. The word algorithm is derived from the name of which mathematician? Alan Turing, Muhammad ibn Musa al-Khwarizmi, I said that wrong, I'm sorry. Named after Abu Yusuf ibn Ishaq al-Kindi, or named after Alonzo Church. A few more seconds to answer. Five, 4. Just checking I've got the right answer. The tension is rising. Jamie's typing the answer. I didn't notice it wasn't here. Oh, I can go lots quicker as well. And the answer for that one was Muhammad ibn Musa al-Khwarizmi. Apologies, Arabic friends, for that terrible pronunciation. I should be better than that. Question 4. Who produces the most ammonia? Put in order from most to least. Who produces the most least? From Russia, China, United States, or India? Who produces the most ammonia? Put them in order. I'm giving you less time because I was being too generous with my time. The correct order. The most is China, then India, then Russia, then the United States. Congratulations if you're in those countries. I don't know. And question 5. True or false? Parts of the brain develop until the age of 26. True or false? I'm hoping they develop until you're about 45. That's what I'm banking on. And it's true. They do. Your brain does develop until the age of 26, which explains at least one of my exes. Don't tell my dad. I hope my dad went for a cup of tea. Question 6. Who coined the term artificial intelligence? Was it robot expert Jasmine Lawrence? Was it the program pioneer Ada Lovelace? Was it computer scientist John McCarthy? Or was it the writer can't speak today. Isaac Asimov. That cocktail. Who was it? Jasmine? Ada Lovelace? John McCarthy? Asimov? Who was it? It was computer scientist John McCarthy. So how did you do? Let us know in the comments. We're very proud of you, however you did. Because even if you did badly, I bet you have skills elsewhere. You will have done completely beautifully. And we are going to have a little bit more of a quiz later on, so do stick around after the next couple of performers. But for now, I keep saying excited, but I genuinely have loved all this performance. So I am excited to have this performer back again. Yolani is from Papua New Guinea. She has a PhD in chemistry and has won 11 awards for her science. I don't even know if she's won them for like tap dancing or dressage or anything. She is going to be talking about 5 goals and a catalyst. So please do whatever you've been doing and welcome Yolani to the stage.
Hi everybody, I want to ask you all a question. Have you taken a bite out of an apple and wondered, where does this come from? Of course, you're probably thinking the fruit and veg section from your local supermarket. But what if I told you that it's, along with other food that is responsible for 50% of the nitrogen content in your body, comes from a chemical reaction that is over 100 years old called the Haber-Bosch process. I will demonstrate the Haber-Bosch process using marshmallows. The Haber-Bosch process is a chemical process that involves combining hydrogen. You see there's 2 hydrogen atoms with a single bond, and nitrogen, 2 nitrogen atoms with a triple bond, over an iron catalyst at a high temperature and pressure to make a simple compound called ammonia. It has 1 nitrogen atom and 3 hydrogen atoms, otherwise known as NH3. The catalyst acts as a magic touch in the reaction to make ammonia. It acts by making the reaction faster. An example of an item that you may have at home that acts as a catalyst is yeast. So why is ammonia important? Ammonia is the key ingredient used in making synthetic fertilizers so farmers can grow our food. Through this process, millions of tons of fertilizers are being made and 40% of the world population is being fed. Unfortunately, this process has disadvantages. It uses great amounts of the world's fossil fuels for energy and as a source of hydrogen. The process pollutes the atmosphere with CO2 emissions, a bad greenhouse gas. Now, the Haber-Bosch process needs to be improved for the greater good of the world so that we can all eat in peace. And that is where my research comes in. My research specializes in catalysts for ammonia production. I make affordable and active catalysts that have the potential in making ammonia in a more cleaner and sustainable way, such as on a small-scale farm like a farm. Now, using renewable energy such as wind and the source of hydrogen to make ammonia coming from water. I aim to minimize the disadvantages in ammonia process while making ammonia, which in turn makes fertilizers and feeds billions of people across the world. Now, I'm sure everyone knows the United Nations. The United Nations has designed and implemented 17 Sustainable Development Goals, specifically to make the world a better place by creating a sustainable future for everyone through addressing global challenges we face today. Now, since ammonia plays a great role in the world for food production, making ammonia should come together with these goals. Now, my research in ammonia synthesis provides fresh perspective into addressing 5 of these goals. Goal 1, no poverty. Goal 2, zero hunger. And goal 7, affordable and clean energy. Goal 9, industrial innovation and infrastructure. And finally, goal 13, climate action. Now, since the last time you saw me in the 2018 Science Slam, I have completed my PhD in chemistry, and I am now Dr. Yalin Upoya. In relation to my research, I've won a total of 11 awards, which includes 2 highly competitive international awards and 1 competitive national award. I've also been honored by the University of Glasgow for my ammonia synthesis research and named 2020 University of Glasgow Future World Changer. I have publications and received recognition and honorable mentions from scientific bodies across the world. I've even had the pleasure of speaking about my research in the Scottish Parliament, meeting different world leaders, and my personal favorite, having tea with Her Majesty Queen Elizabeth II in her Hollywood Palace. That was a brief insight into my research, and I hope you enjoyed my talk titled 5 Goals and a Catalyst. Thank you.
Thank you so much. And I love that you were like, a word. I'm a badass. I've done so much stuff. Also, the Queen has tea with me. Absolutely amazing. Thank you so much for that. It's amazing to hear how brilliant you're doing after completing your PhD. Congratulations. And now it's time for our final performer who joined us in the 2016 Slam. Leon combined neuroscience and psychology and marketing, and he's going to be talking to us today about why choosing between caramel and chocolate might be a little bit trickier for your brain than you might expect. Do whatever you've been doing as we welcome Leon to the stage. That was my slight hesitation. I'm just checking he's there. I'm going to keep smiling. I'm a professional. I think he's here. There we go.
When was the last time you went to the supermarket? Just yesterday, I wanted to get a really, really nice chocolatey ice cream after a long day at work. But you know what you're thinking? Don't judge me, come on. So I put on my face mask and cleaned my hands with loads of hand sanitizer, and then so here we go, and cleaned my hands with loads of hand sanitizer, and then I ended up feeling overwhelmed with the sheer amount of overwhelming tempting choices at the supermarket. So these products are all optimized to grab your attention, but for some people the choice is a bit trickier than for others. I know this is kind of like they're not greedy or they want it all, but simply because all these visual product information can overwhelm their brain. Processing all cues that are thrown at people with dyslexia quickly enough so they can keep up with the pushy speed of the supermarket, that can be difficult. Essentially, not all of our brains work the same way. Some work differently. So imagine you're standing in front of the huge supermarket's fridge, and you can feel the sugar breathe down your neck. You can feel the pressure to grab an ice cream right now. So this is a tricky situation, really. And this makes you go for the really most prominent package there that shows some chocolatey ice cream on the cover. But actually, damn, too late. You just grabbed this bounty, disgusting coconut flavor, and you didn't even have the time to read. So think about the pressure you felt in that situation without any dyslexia. But with dyslexia, it could be even way worse. So maybe for you, dyslexia means jumbled letters and bad spelling. So picking just the wrong flavor in the supermarket, that's a little annoying detail. But, issues with dyslexia are more common and far-reaching than that. To give you an idea, 1 in every 6 people watching live right now, and up to 11 million people in the UK may be affected by such decisions during the shopping trip because of dyslexia. Therefore, I bet you know someone with it. Well, if you didn't, now you do. It is my privilege to stand here today as one member of this large group. I was fortunate enough to get diagnosed at a really young age, and these experiences turned me into an advocate of the special strength of a dyslexic brain. That led to the Science Slam presentation in 2016, actually, and why the brain can be richer. So basically here, as an advocate, I fought my first scientific battle against nasty little visual information presented in italicized font in contracts. After demonstrating that this font style hinders the reading for people with dyslexia, I also showed that specific dyslexia helper fonts can make text more readable. but for everyone. In my second scientific battle for a more inclusive society, also called a postdoc in Montreal right now, I'm discovering ways in which the marketing of supermarket products can help dyslexics to make better processed visual information and to increase their decision-making capacity. Trust me, no one wants to end up with the wrong flavor just by accident. So how do we do that? We actually focus on your mental workload and the effects that this mental workload can have on you during the shopping trip and decision-making in general in that specific moment. So let's jump right from theory into practice. I want you to do a simple calculation in your head without any helpers. Just as shown up here, calculate 154 minus 37. You got 5 seconds. Great. I'm sure you all arrived at the solution of 117. So now we're going to do a second calculation. In your head, just do 169 minus 37. You got 5 seconds. Go. All right. I'm sure now it was much harder for you to focus on the calculation and much harder to arrive at the result of 132. What we simulated just here was neural noise. That is spontaneous brain activation that can lead and distract during information process. This phenomenon can even affect your shopping trip. So all the cues on packaging can seem quite overwhelming. Your brain is already processing internal noise. Internal noise is the equivalent of the songs in different songs you just heard right there. Therefore, we try to find ways to lower the volume so that everyone can improve the processing of visual cues and make better personal decisions. So what you can do next time you go to the supermarket is pay attention to all the different cues you're using for picking out your products. And also notice how much more information there is that your brain renders irrelevant for you and that is filtered out. This is the key challenge of the dyslexic brain and the subject of my campaign. By the way, I went for a triple chocolate.
Thank you so much, Leon. Triple chocolate. That is a fantastic choice. Beautifully done. We are going to just round things off now with a little few extra quiz questions. So it'll be the same thing as before. In the chat box, there will be a link that you can click through and play along. I promise I'll go a lot quicker this time. Or at your screen, your housemates, wake up your children. Just yell it at them because they need to know about science. This is important. This is education. And so I'll give everyone a wee moment just to click on the link or decide how you are going to play along. Okay, is everyone with us? Question number 1. Which is the furthest east, Carlisle or Edinburgh? May not have been the answer you were expecting. The answer is Carlisle. What? Queries in the chat box. We will come to everything later. Question number 2. Everyone's with us. What colour is deoxygenated human blood? Red, blue, yellow, or green? Have you selected one? It's a good way to tell when people are back in the dating world that you are genuinely dating a human. You check their deoxygenated blood and confirm that it is red. That is the colour it should be. If not, run for the hills. Question number 3. In graph theory, what term is used to refer to the components of the image below. I realise if you're not playing along, you may not understand this. Just take a wild guess. Is it circles and lines, nodes and rules, vertices and edges, or circles and edges? Which sounds like the name of a 70s folk album. Hey, where this is circles and edges, it's just really about a hard time in my life. Like, that's what life is, man. It's circles and edges. You know? The answer is, unfortunately, not that folk bad. It is vertices and edges. Question number 4. We're back on ammonia. True or false? Ammonia is flammable. Is that true or false? Don't immediately try this in your home. Take a guess. Okay. The answer is true. Ammonia is not highly flammable, but containers of ammonia may expose when exposed to high heat. And I feel whoever wrote that question and answer is writing that from experience. These were all written by our Sci Slammers, and I feel, Lewis, was that you? Did you learn a life lesson finding that out? Question number 5. In what year was the specific learning disorder dyslexia first described? Inspired by Leon's presentation just then. Was it 1833? It's when my dad was born. See if he's still watching. 1896, 1921, or 1954, which was 10 years before the release of Circles and Edges. The answer is 1896. There we go, Queen Victoria's time. And finally, question number 6. True or false? Tech addiction coach is a typical job related to artificial intelligence. Tech addiction coach. That is true. There is someone out there who can help you with your Candy Crush issues if you need them. Let us know how you did in the comments. I know we had some very victorious people there before. We would love to hear how you're doing. And thank you so much for joining us. Just before we go, we are going to head over for a quick I don't know where I'm pointing to Heather Lambie from the University of Glasgow Graduate School of Science and Engineering, just for a quick word. So Heather, over to you.
Thank you so much, Jan. I feel a bit like I'm reading the news here. So anyway, this is our first ever Science Slam alumni event. I hope it is not our last. Our presenters have been fantastic, so thanks to them all for agreeing to contribute to this event. I just want to say thanks as well to Jamie, who has been running the all behind the scenes as our producer. So thanks, Jamie, and thanks also Sian, who has hosted this event from the very start, and we couldn't do it without either of you. So thank you very much. It's really nice that we can come together as part of a community and that we can see so many people here tonight who have been to the events throughout the years, but also that we can reach so many new people as well. So thank you all very much for watching.
Thank you so much, Heather. And can I do a special shout out to someone whose real name I assume is Jay, who in the comments has said that you can explode anything if you try hard enough. I mean, that's true, but let's not explore that during lockdown. That's a maybe phase 4 kind of activity. As Heather said, huge thank you to everyone who made this happen, all of the incredible presenters. I love all your work so much. I'm so glad you're making the world better. Thank you to Heather and to the School of Engineering. I can remember how to say it in the right order. The Graduate School of Science and Engineering for looking after us, and for Jamie for doing such an amazing job on the tech, and to all of you for watching. It's been an absolute pleasure spending our evening with you. I hope that you feel inspired, I hope you feel connected, and I hope that we get to see you wherever you are in the real world before too long. Thank you so much and good night.